Good. Well, first I want to thank Chris and Slava and Ann for organizing this meeting and for inviting me to speak. It's always nice to be back at Harvard. I was here as a graduate student many decades ago. And it's also very nice to be able to interact with old friends. Well, as our previous speaker mentioned, some of us, including myself, have been at this game, that is electron-molecule collisions, for quite some time, decades, in fact. And I was fortunate enough to be a postdoc at Caltech at what I consider to be basically the formative period from a theoretical point of view for basically what was the beginnings of ab initio electron-molecule collision theory. And so that tremendous amount of activity took place through a period that basically started in the early to mid-70s and then continued for another decade or so. Many methods, we were naive in those days. Many methods were proposed. Some have gone the way of the dinosaurs. A few of the more robust methods have thrived and have been developed into real computational tools. Vince mentioned the Schwinger method. We developed variational methods based on the cone principle. There's R-matrix methods, linear algebraic methods. Of course, there are a lot of early methods. We were naive, so we thought that purely L2 approaches would work and we could just completely ignore scattering boundary conditions. Those methods have not survived. But anyway, so when I was putting this talk together, I took basically a different tack than Vince did. Vince tried to give you some perspective on the field by surveying a lot of his recent work and using that as an opportunity to point out what the pitfalls are, what kinds of things we know how to do pretty well, where we still need a lot more work. And so I really want to give you some of the same message, but rather than survey a lot of work, I want to concentrate just on one system in particular. And it's actually a system that we thought we understood pretty well. But I want to show you that even with a system as basic as CO2, now let me turn on my screen, there's still a lot we have to learn. So the title of my talk is The Dynamics of Resonant Electron Collisions with Carbon Dioxide. Before I go any further, let me acknowledge two collaborators who have been heavily involved in this work. It's been going on for the last year or so. Dan Haxton, who is here, who's speaking tomorrow, I think, or Wednesday, and Bill McCurdy, who unfortunately can't be here because he had teaching responsibilities that didn't make it possible for him to be here. All right, so I said this is going to be a new look at a very old problem. And I think it's safe to say that with the possible exception of molecular nitrogen, no target molecule has received more experimental and theoretical attention over the decades than has CO2. The principal features of low-energy electron CO2 collisions have been known and studied for over 40 years. And in fact, some of the earliest experiments on CO2 were done in transport measurements were actually done in the 1930s. So, with that history, what is the source of the renewed interest in this problem? And I'm trying to convince you that there is some interest in this problem. There's basically two things that prompted us to look at this. One is I think I'm going to try and convince you that in spite of all the work on CO2 and CO2 minus, there are still significant gaps in the extant literature on various key aspects of the subject. But what that's really fair to say in retrospect, what really got us interested is that we have an experimental effort in this area on dissociative electron attachment that both at the LBL and we have collaborators at Auburn University. And they've been doing recent work over the last 2 years on CO2, and they presented us with some really challenging theoretical questions posed by their most recent measurements. All right, so for those of you who are not wedded to this problem like I have been for the last 15 years, let me start with a sort of a primer on the principal features of electron CO2 collisions. Now, as I say, it's been known since the early 30s that the integral cross-section is dominated by two prominent features. These are now just measurements of the total elastic scattering cross-section. There is a dramatic rise in the cross-section below 2 eV, and then there is this prominent resonance peak centered at about 3 volts. And this work was taken from a paper that one of our graduate students did some 13 years ago. You can see there's several calculations, with the exception of the higher energy one. Basically, all of the theoretical calculations, at least for elastic scattering, got the resonance position in the right place. The difference between the various calculations, why some are broader and it seemed to show the peak broader and seemed to agree better with the experiment than the other ones did, is just a question of whether or not the calculation was done at one fixed nuclear distance, or whether there was an attempt to do that as a function of R and then convolute the ab initio data over the vibrational ground state of CO2. But we basically understand that. And there again, we also get the low energy rise in the cross section, right, if you put in polarization and do a very careful calculation. So that's one feature. The other feature is that this 4-volt resonance also gives rise to prominent resonant vibrational excitation structure, and that structure actually shows these oscillations, which we all know is we call it boomerang structure right now. It has to do with it's a careful balance of what the negative ion potential curve is and the lifetime of the resonance. So if an electron can get trapped in one of these resonances and live for more than 1 or 2 vibrational periods, then it has a chance to build up these interference resonances. And so this is a study we did about a little over 10 years ago, where we're comparing our theoretical calculations with these beautiful experiments of Michael Allen, in which he actually resolved the Fermi dyad. Basically, there's an accidental degeneracy between two quanta of bending motion and one of symmetric stretch in CO2. And because of that overlap, the states are split, and it's called Fermi resonance. And so you can see we get that structure and that splitting essentially perfectly. All right. The third part of this review, this primer, has to do with threshold vibrational excitation of those same Fermi dyads, or in case or even more higher levels of excitation, the triads, polyads, whatnot. Those vibrational excitation cross sections show anomalous behavior. There are cusps at the thresholds for these various vibrational resonances at very low energy, and they also show this structure. And that, again, we're comparing with Michael Allen's beautiful experiments and some work that Wim van Rosse, who at the time, in 2004, was a postdoc, he's since gone on, he's a professor at the University of Antwerp. And so it's sort of a effective extension of effective range theory with the inclusion of non-local effects kind of describes that phenomenon as well, too. All right. So all of these phenomena that I've explained, mentioned so far, the threshold vibrational excitation, the rapid rise in total cross-section below 2 eV, the shape resonance near 4 volts, and its accompanying resonant vibrational excitation. All of these can be properly understood in terms of a doublet sigma, these are negative ion states now, a doublet sigma virtual state at low energies, and this doublet pi shape resonance, which of course at linear geometry is doubly degenerate, and there's this boomerang structure that one sees in the vibrational excitation is a consequence of the very strong Renner-Taylor coupling between the two components of the doublet pi state when it bends back and forth around its linear geometry. Okay, now the second part of the story, and what really got us involved in this, is electron CO2 dissociative electron attachment. Now it turns out that the thermodynamic threshold for dissociative attachment in CO2 is 4 volts, which is precisely the energy where this doublet pi U shape resonance is. And so I think it's pretty clear that since there's no other negative ion resonances in the vicinity, it's the 4 eV shape resonance that also feeds this dissociative electron attachment channel. And as I'll show you in a minute, there's some problems understanding, even just coming to grips with that, how that can be the case. There's also a dominant, at least at room temperature, the most important channel for dissociative electron attachment is at 8 volts. So the 8 volt dominates, the 8 volt channel dominates, and there are higher, there's a third peak at much higher energy, but I'm not going to talk about it. It's around between 12 and 14 volts, because as you can see, if you put it on the same scale of here, I have to multiply it by a factor of 10, so it's really not, it doesn't really compete as a dominant channel with 2 lower DEA resonances. It's been known for a while that the 8 eV channel, when you look at the kinetic energy of the fragment CO and O- that's produced, you basically get a bimodal distribution. So in addition to this, the hot fragments coming out, there's quite a bit of vibrational energy in the CO fragment here. If you work it out, it's not something like an average nu of 13 to 15 or something like that that comes out in this channel. But in addition to that, there's a very low zero energy peak, which basically produces cold CO plus O-. And so it's kind of a challenge to understand where that comes from. Okay, so is there a way to tie all of this data together? And so what I'd like to say is, do we have, at this point in time, do we have a self-consistent view of electron CO2 collisions, at least the resonant collisions, because these are all negative ion resonance processes that I'm talking about. And when I say do we have a consistent view, what I mean is do we have a knowledge of the relevant neutral and anion states and the dynamical mechanisms that explain all of this observed data. And if we finally do, and I claim we almost do at this point, why has it taken so long to develop this consistent view, given that formal resonance theory, which can explain all of this stuff, has been developed decades ago, essentially, starting with the early work of people like Norman Bardsley and Herzenberg back in the 60s, and Tom O'Malley. Well, I maintain that the progress in understanding electron-CO2 collisions has been impeded first by a number of long-standing misconceptions that are in the literature. That's one problem. The other problem is the fact that the electron scattering collision theory of resonant scattering that explains these phenomena has focused over the years on developing more and more sophisticated resonance models, non-local models of increasing complexity, with little attention paid to the role of multidimensional dynamics in the dissociation. And as I'm going to try and convince you, to understand electron CO2 dissociation processes, the problem is fundamentally multidimensional. Okay, some CO2 minus basics. Obviously, the ground state of CO2 in equilibrium is linear. The CO2 minus anion is in fact electronically bound with an equilibrium angle of somewhere around 138 degrees. That's been known, it's an experimental fact that's been known for decades. I've already mentioned that the thermodynamic threshold for producing ground state CO plus O minus, by dissociative electron attachment in this case, is about 4 volts, very close to where the doublet pi u CO2 shape resonance is. Again, at the equilibrium CO2 geometry. Now, the other thing that's important is that the threshold, the thermodynamic threshold for producing electronically excited CO plus O minus is about 10 volts. And therefore, both of these prominent DEA peaks at 4 and 8 can only produce ground state products. And I'll show you that leads to to a paradox. Okay, so I said there were some misconceptions. Let me go through those. Misconception number 1. The misconception that's been in the literature for a long time is that the 4 volt negative ion shape resonance, doublet pi u, which is unbound in equilibrium, actually becomes bound. It becomes the bound ground state of CO2 minus when the molecule is bent. Okay? So before I pursue that a little bit, let me remind you that carbon monoxide, of course, is a singlet sigma closed shell ground state. So that's spin 0. O minus, on the other hand, is its ground state is doublet p, which means it's triply degenerate. And therefore, when you try and make CO2 minus anion states out of neutral CO and ground state O minus, you can necessarily only form 3 states. If I bring those together in linear geometry, basically I have 3 ways of orienting a doublet p, either 2 degenerate ways if I orient it perpendicular to the CO axis, and then a 3rd way if I orient it parallel to the C axis. So in linear geometry, as these come together, I can only get a non-degenerate, or at least electronically non-degenerate, doublet sigma state, and then a doubly degenerate doublet pi. So there's 3 states. Okay. Well, in 2004, Thomas Sommerfeld, who was at the time a graduate student of Lawrence Saterbaum's, pointed out that it was not, in fact, the doublet pi u state of CO2 minus that becomes bound upon bending, but it was, in fact, this doublet sigma state. And here you can see cuts through this surface. This is the function of, this is just a study of CO2 minus as a function of symmetric stretch. Okay, so when you bring the molecule, the negative ion and the neutral together in linear geometry, you have a doubly degenerate dotted line here. That's the doublet pi state. And then below that is this doublet sigma state, which in fact becomes the virtual state that explains all this low energy phenomena below 2 volts. But when you bend it, the pi states split into 2 non-degenerate components, but the sigma state is the one that becomes bound. And if you follow this, you can follow it all the way adiabatically to the ground state well of CO2 minus. And there's no question that it's the sigma state, the virtual state, that is in fact responsible for making bound CO2 minus. Okay, so that's one misconception. I'll show you why these misconceptions are important in unscrambling the dynamics in a moment. The second misconception was that the 8-volt DEA feature, that's the prominent peak at 8 volts for dissociative electron attachment, was the result of a doublet sigma shape resonance. Here's an early paper. This is one of the first theoretical studies of this subject by Clayton, Jerry Siegel, and Howard Taylor back in 1970. And here's their, they calculated, they used a stabilization method basically to get these negative ion curves. They show the ground state of neutral CO2. They show the CO2 minus doublet pi state, which was responsible for the 4 eV resonance in the Frank-Condon region. And then they have this doublet sigma G minus going up to 8 volts. But of course we know now that that doublet sigma G state is in fact the virtual state, points down, and becomes unbound at smaller internuclear distances. Okay. In fact, yeah, mine's red. It doesn't work. This is better. We showed about a little over a year ago that in fact this ADV feature that's responsible for the 8-volt peak in dissociative attachment is in fact a doublet pi G Feshbach resonance, not a shape resonance, whose parent is the lowest triplet pi G state of CO2. This was a joint study with our experimental colleagues at LBL, and it appeared in JFSB around a little over a year ago. So it's a pi state that's causing this 8-volt resonance. So now we have a problem. Now there's a paradox. And that is, now we've got too many states. Here again, I'm dumping on all these previous workers who have looked at this. This is an older paper by Leon Sanch and collaborators, which, again, like the Siegel paper, showed negative ion curves that are supposedly responsible for all these resonances. Here's the doublet pi U shape resonance. Here's a sigma state, which we now know is misplaced. It should go down here and become a virtual state. But they do show this doublet pi G shape resonance, Feshbach resonance at 8 volts. Okay, now, many years ago when I was a young staff scientist at Livermore, I was being evaluated by one of our administrators, and he was looking over what I had done over the last year, and he was impressed by the number of publications coming out of our group, and he said, well, some of us may have forgotten a long time ago how to read, but we still know how to count. And so I looked at that. I never forgot that. I know how to count. A pi state is doubly degenerate. There's another pi state that's doubly degenerate. And a sigma state, that's 5 states. Going to an asymptote, as I showed you before, can only have three states coming out of it. So something's wrong with this picture. Okay, well, we also figured that out. And the answer, of course, is that there's got to be a conical intersection between the CO2 minus shape resonance and the CO2 minus Feshbach resonance. So they intersect somewhere at large. This is now not symmetric stretch. This is keeping one CO distance fixed at its equilibrium geometry and pulling off the other oxygen. There's a conical intersection out at about 3.5 Bohr. Okay, and that of course explains how everything's coming. If you track the shape resonance to its asymptotic limit, you in fact produce CO minus, which is a unbound shape resonance, plus oxygen, excited oxygen in singlet D state. But the Feshbach resonance, on the other hand, dissociates to ground state products, CO plus O minus. So there's that conical intersection. And the fact that that conical intersection occurs at stretch distances, and it's also slightly bent. There's actually two seams of conical intersection out there because of course once you start to bend this thing, the doublet pi states split into non-degenerate pairs. So you get an A prime seam and an A double prime seam. They both occur fairly close to linear geometry, but at stretch distances. So that explains why the CO comes out hot from these transitions and not. There's still a problem. We really still don't really understand that bimodal. We understand why the big peak, the main peak, is vibrationally hot CO. We still don't really understand where the cold CO is coming from. But that's a different story. Okay. Now, second paradox. This is the 4-volt resonance. This is what the current. This is now I should say is still a work in progress. This is really a hard problem. As I said, the 4-volt resonance, which is also, been studied ad infinitum with respect to vibrational excitation with its boomerang structure, etc. It's that same resonance that feeds dissociative attachment. Now, in a simple one-dimensional picture, the CO2 minus as a function of stretch sits in a well, right? So you put a wave packet up here, and it travels down and it bounces off this outer wall and it comes back, and that's where vibrational excitation comes from. And since it can survive for more than 1 or 2 bounces, that's why you get all these vibrational structures on top of this resonance peak. So how can that same resonance feed a DEA channel when it's not even obvious that there's an asymptote for it to go to? Okay? And furthermore, this is what really got us interested. Our experimental colleagues came to us with the angular distributions that they had measured in a Coultron's apparatus for this process. And the dissociative attachment peak is got a minimum at 90 degrees, and its maxima occur at forward and backward directions, which is precisely the opposite of what you would expect for a pi resonance. Because a pi resonance, basically would be maximum at 90 degrees and be 0 in the forward and backward directions. So what's going on there? So here, now let me say a few words. You're going to hear a lot more about this tomorrow from Dan Haxton about angular distributions. We can get at the angular distribution associated with dissociative attachment by basically going back to the equations that we used to do this resonance scattering. This is the so-called local complex potential model. This is the sort of a driven Schrodinger equation, and the driving term is basically what you would call the square root of gamma, the square root of the width. And it's basically a bound free matrix element between the resonance wave function, the electronic Hamiltonian, and the background function and the resonance. Now, under certain conditions, if the resonance is steeply dissociative and axial recoil, which you all understand what axial recoil is as a result of having listened to Bob Lucchese earlier. Under those conditions, this driving term factors into a term that only depends on the internal coordinates of the negative ion and an angular term which basically tells you the angular distribution in the body, in the laboratory frame. Okay, you can get that by basically, if you have an ab initio calculation where you got these so-called entrance amplitudes from, you can do a multi-channel analysis. You need the partial widths, and total widths, and everything, and then you can basically extract that angular function. So for the case of CO2, it looks like this. The 4-volt pipe resonance is basically a combination of F wave and P wave. The P wave component is here. The F wave is dominant. This is a 3D image which basically tells you the probability of an electron attaching to a fixed CO2 molecule in linear geometry. And you can use this basically to predict, if you assume that the molecule dissociates axially, no matter how the electron attaches, it dissociates axially, then you would predict an angular distribution that looks like this, which is of course the inverse of what they measure. Right? So here it's 0 in the forward and backward direction, and with strong peaks at 30 and 150 degrees. All right. You can still use that axial recoil treatment if you assume that the molecule, after the attachment probability, if the molecule bends before it dissociates axially, then you can sort of convolute that bending motion with the attachment probability and plot out what the angular distributions would look like as a function of where this thing bends before it dissociates. And you can see at about 150 degrees, which is 30 degrees off linear, which is what the experiment shows is happening, you get a distribution that looks pretty much like what these guys measured. So the trick is, though, is that this only works if you assume the molecule bends and then dissociates on one component of the resonant surface, A prime, not A double prime. Okay, so again, conical intersections, as we see, are going to be key to understanding this. So I want to say a little bit now, why does the molecule seem to want to dissociate on the A prime surface rather than the A double prime surface? This is the resonance energy and width for the A prime and well, in symmetric stretch, B1, which becomes A double prime when you allow the bond distance to be different. And you can see that when the molecule bends, the electron wants to, the width grows really, really rapidly, and so the electron comes off very, very fast. It just auto-attaches. Whereas in B1, the width is very small and doesn't depend very strongly on geometry. So you would say, well, okay, well, maybe it depends. Maybe something's wrong. Maybe this would predict that the thing would dissociate on the A double prime surface because that's where the survivor probability would be greatest. Well, and there are in fact conical intersections between the Feshbach resonance and the shape resonance in C2V symmetry. These have nothing to do with the conical intersections that are responsible for the 8-volt resonance. These are conical intersections at much lower energy. So these, in principle, can be reached starting with a 4-volt resonance. Okay. Well, the reason that the A double prime surface plays a very small role in all of this is because in order to reach that region of conical intersection, which is necessary to get to these ground state asymptotes, there's a barrier. And there's no way to reach this without going through a barrier, whether there's no combination of stretching and bending that'll get you there on the A double prime surface. And these are heavy atoms when they dissociate, and they're not going to tunnel through a barrier like this. So that explains at least why the A prime surface seems to be the candidate. Now, there's another possibility. There's also a path to dissociation via the 4-volt resonance that involves the only other component of the negative ion which can reach the asymptote, and that's the virtual state. And we have also found the seam of conical intersection between the doublet sigma G virtual state and the shape resonance. And there it is out there. These are monstrous calculations. These are configuration interaction calculations on the order of 16 or 20 million configurations in order to locate these things accurately. Okay, so that would also say that it's possible that this molecule stretches symmetrically and then reaches this conical intersection with the virtual state before it dissociates. Okay, so we've identified two viable paths to dissociation at 4 volts. the sort of semi-empirical axial recoil model can't distinguish between the two, and both of them are viable paths that seem to agree very well with experiment. In order to complete this picture, we're actually going to need the complete three-dimensional surfaces for all these negative ions and do detailed dynamics to determine whether one or the both of these paths are playing the dominant role. All right, so let me summarize. I think I'm probably over right now. This is what we know about CO2. The lowest anion state, doublet sigma g, which is a virtual state near the equilibrium geometry of CO2, is what's responsible for the rapid rise in the elastic cross-section and the anomalous threshold behavior seen in the vibrational excitation of the Fermi polyanions. The doublet pi-u anion state, on the other hand, is responsible for resonant vibrational excitation, and the boomerang structure is the result of the strong Renner-Teller coupling between its two components when it breaks linear geometry. The 8-volt dissociative attachment resonance is in fact a doublet pi-g Feshbach resonance associated, whose parent is the first excited triplet state of the molecule, and it has a conical intersection with the shape resonances at large asymmetric geometries, which allows it to feed the 8-volt DEA channel. And then finally, we've identified two more important conical intersections that explain how the 4-volt resonances also produces ground state products in dissociative attachment. But at this point, we are not in the position to say which of those two pathways is more important. But the take-home message in all of this is that in order to understand all these processes in CO2, the dynamical treatment involves conical intersections and is intrinsically multidimensional. Okay, so with that, I think I'll stop.
Any further questions? No?
See, several slides back, you had a potential with the CO2 and the CO2 minus. And you had the CO2 minus about 2 volts above the CO2. Was earlier than that. Earlier. The CO2 minus was about 2 volts above the CO2. Was that just stretch and you weren't allowing for bend right there?
Oh, that was stretch, yes.
Okay, so there's no bend in
Not in the curves I showed. The only thing that shows the bend is these pictures. I should say, it is really hard. This is another problem with electron-molecule scattering. We're necessarily forced to treat the n+1 electron problem, that is the electron plus neutral, in terms of the target states of the neutral. And so in a sense, it's like calculating electron affinities. So you do a really good calculation on the negative ion, and you may get the shape of these things right. You carefully make the calculation size consistent. But the absolute positioning of the negative ion states relative to the neutrals is almost impossible to get right. So we do some empirical, if there's something we can, if we know the asymptotic splittings or we know where a resonance should be, we adjust the curves accordingly. So they could be self-consistent, but not consistent with respect to the absolute energy.
So there's only about half a volt difference in the energy between the bent CO2 minus and the linear CO2.
That's right.
So if you were to stick a few argon atoms on this, like Mark Johnson does,
yeah,
you would turn the anion into a real bound state. Should one then view that as being derived from the virtual state?
You say you would turn this into a bound state at equilibrium geometry?
Actually, the bent CO2 minus will be below any point on the neutral surface if you put a few argons on this.
Oh, yeah.
And so now you have a really, truly bound anion. Should I think about this as being derived from the valence pi star?
No, you should not. You should
still think
absolutely
about it as being derived from the virtual state?
Yes, you should.
Isn't the virtual state pretty diffuse?
The virtual state is almost impossible to locate because it's a sigma state. There's no potential barrier, so you can only characterize it in the region where it's electronically bound.
Right. Yeah, but this species is going to be pretty localized.
Well, sure. The anion state is very well localized once you pass to the right of the crossing point with the neutral. I mean, it's right in the crossing region. It gets very diffuse, but as soon as you can move away from that region, it's a bound state. It's very easy to describe. And so, you know, if you have some way of stabilizing that, you just pull that thing down. It's sort of like F2 and F2 minus, you know. F2 minus is electronically very stable. It's a bound negative ion, but when at the equilibrium geometry of F2, it's very, very close. So if you have some way of stabilizing that, you'd keep it bound for, you know, at all infinite distances. It's only hard to describe. It's not bound.
Yeah, I just want to comment on this, on your question. We had this Hartmut Kotov in Kaiserslautern did experiments on attachment to CO2 clusters, and you can see how this virtual state stabilizes when you add more molecular units to the cluster. You have transition from the virtual state to the bound state,
right.
And you can see this bound state in electron attachment.
Well, this is tricky because in this, if you have two CO2 molecules, the electron is shared between the two of them. It's not localized.
So
on
two
one.
CO2, I don't know. Yeah. you need at least, I think, 3 or 4.
Yeah, then it localizes. Then it localizes back onto one. But that was shown by Mike Johnson.
Well,
so if you have a small number of CO2s, the electron is on a dimer.
yeah.
But if you build up enough CO2s, it switches over to actually being back on a single CO2.
Oh, well, there are different states. Some of them are diffuse. You can see them in electron attachment experiments.
This is the ground state.
Yeah, the ground state. Yeah. They appear as vibrational Hertzberg resonance. And you can actually, by measuring their position, you can see what is the binding energy of the states. And they are diffuse, they are not localized.
Well, let's chat about that.
Yeah, sure.
We have boxing gloves set aside.